All life on Earth is supported by the sun. This amazing resource radiates energy and provides us both heat and light by fusing hydrogen into helium at its core. We call this solar radiation. Only about half of this solar radiation makes it to the Earth's surface. The rest is either absorbed or reflected by clouds and the atmosphere. Still, we receive enough power from the sun to meet the power demands of all mankind, millions of times over. Solar energy, power from the sun, is a vast, inexhaustible, and clean resource. Sunlight, or solar energy, can be used directly for heating and lighting homes and businesses, for generating electricity, and for hot water heating, solar cooling, and a variety of other commercial and industrial uses. Most critical, given the growing concern over climate change, is the fact that solar electricity generation represents a clean alternative to electricity from fossil fuels, with no air and water pollution, no global warming pollution, no risks of electricity price spikes, and no threats to our public health. The solar resource is enormous. According to the U.S. Department of Energy, the amount of sunlight that strikes the Earth's surface in an hour and a half is enough to handle the entire world's energy consumption for a full year. Just 18 days of sunshine on Earth contains the same amount of energy as is stored in all of the planet's reserves of coal, oil, and natural gas. And, once a system is in place to harness the solar resource and convert it into useful energy, the fuel is free.
Let me bring this amount of solar energy down to numbers that are more relevant to us. The National Renewable Energy Lab has collected information on how much sunlight energy you get in various locations in the United States. Now, there's also other agencies in other countries that collect this kind of information for their countries. For 30 years, NREL, the National Renewable Energy Lab, collected this data at 250 stations sprinkled around the country. Bottom line of this is that the amount of sunlight energy doesn't vary a huge amount across the country. Of course, the Southwest United States has more than the Northeast, but it's not double. It's maybe 40% more. So Seattle, which is probably the least sunny spot, gets about 60% of what Phoenix gets, which is the sunniest spot. Buffalo gets 73% of the amount of sun that San Diego gets. Now, when I say amount of sun, I'm really speaking about kilowatt hours per square meter per year, or also called full sun hours per year. This is a measure of energy that's falling, not how many clouds are in the sky. But a day that has a few clouds in the sky can still have a lot of energy falling on your solar panels. So NREL is measuring the energy that you get. Germany is one of the world leaders in solar energy use and solar power deployment. Having fewer kilowatt hours per square meter just means that you need a little bit larger area of solar panels to get the same amount of kilowatt hours. That has become less and less of an issue as the cost of those panels has gotten lower and lower. So to put that on a map, this is just to give you a visual of how sunny or not sunny Germany is, even though they're the world leader. And also it shows you that the solar resource is pretty uniform across a vast area of the country. This is really different than wind. Wind is really site specific. Here's the world leaderboard as of 2018. China has taken over the leadership position as far as total installed capacity. That's actually relatively new. For a long time, Germany was up there too. And the United States, whew, finally, we're getting up there as far as the total installed capacity. But we are still, both China and the United States, we're far, far behind as far as the per capita, per person amount of solar, and Germany is still number one as far as that goes. The good news, though, is that this leaderboard thing, this is going to change. This is going to change a lot in the next few years because, for example, Arizona, which is incredibly sunny, they are waking up to installing a lot more solar power plants out there, and they have a lot of physical space as well as a ton of sun. Okay, so we have the resource, we have the solar resource. What about the physical area that it takes? If you have about 12,000 square kilometer equivalent of solar panels for the United States, that would generate all the electricity we need right now. So that's about the size of the Nevada test site and range. So it's not that huge. Now, of course, you wouldn't put it all in one place. You sprinkle it around where you need it. And I also have a little graph up here about how much it takes to power the whole planet. And that is 7/10%. I mean, it's a tiny, tiny amount to power the whole planet with solar cells. I'd put a caveat up that, yes, we'll eventually need storage. The perception of renewable energy in both wind and solar is these are intermittent. You get solar electricity when there's sun, you get wind electricity when there's wind. What happens when you don't have those? That's an issue. The first way to solve that is to essentially, as you build more and more of those kinds of power plants, the intermittency gets less and less because something is going to be online. And now what's happened is that the costs are so low that you can actually build a lot more than you need at any one moment so that something is always working. It's a little bit like the internet. The internet is made of nodes of computers, and it's a rare thing to have a widespread internet outage because you have so many pieces to it that something is always working. And in the beginning, it was a network of computers. Now it's a network of servers, and now it's a network of server farms. Okay, so these networks are getting bigger, and we're doing the same thing with electricity now. We're growing our internet of electricity, and that's also a more robust system than a system that has lots of centralized power plants. If you have centralized power plants, if you take out one big one, then you can have a widespread outage. But if you have lots of little ones, then that's actually better for our electricity, the security of our source of electricity. So that's the first thing. You overbuild, and they're starting to do that, to have more capacity than you need at any one moment, so that when the wind's not blowing over here, you can still have this turbine over there working or this solar farm working over there to supply electricity. And that is going to reduce the problem of intermittency. Then the next thing you do is add energy storage, a la batteries. So it's kind of interesting. The evolution of things has been that we started out using off-grids that all had to have batteries, and we kind of evolved into where we had pure grid ties that didn't have batteries. And now we're going back to using some batteries for various things. Not so much that we need them in our houses necessarily, but utilities are installing batteries to have a steady source if they charge those batteries with wind and solar. Right now, what they're using the batteries for is to shave their peaks, so that that just reduces the number of these gas-fired power plants that you have to have on standby, which of course is expensive. So they're starting to do that. For your house, we're seeing people are more interested in backup power. So they don't need the batteries all the time, but if the utility's down, they can have backup power. In the long run, though, we're going to have more battery on the grid to handle the intermittency issue. And the good news is that batteries is now a growth industry. So for a long time, batteries, we were kind of stuck with lead-acid batteries. And they were heavy and expensive, and they didn't make a lot of real big ones. So the lithium-ion battery came into play, I don't even know, 30 years ago. And it started to feed the electronics industry. So all our cell phones and computers all have lithium-ion. What's happened in recent times is the rise of the electric vehicle. So now we have electric vehicles that's another industry people aren't paying a lot of attention to, but it's growing like topsy. The batteries for those are also being perfected. They're being mass produced. So now we're in a position to be able to have large-scale battery storage at a reasonable cost. And again, it's a cost thing. Technology's been there a long time, but you got to mass produce it to make it affordable.